Welcome to Daily Papers, the podcast where we break down the latest and most interesting research papers into bite-sized conversations.
Today, we've got a paper that sounds like it's straight out of a sci-fi movie. It's titled KungfuBot, Physics-Based Humanoid Whole-Body Control for Learning Highly Dynamic Skills.
KungfuBot, you have my attention. So, are we talking about robots that can actually perform martial arts?
That's exactly what we're talking about. The goal of this research is to get humanoid robots, the ones that look like people, to imitate really complex, fast, and dynamic human movements like kung fu or even dancing.
That sounds incredibly difficult. I feel like most of the robots I see are still a bit, let's say, clumsy. They can walk, maybe pick up a box, but a jump kick seems like a whole other level.
It is, and that's the core problem the researchers are tackling. You'd think you could just show a robot a video of a person doing a move and tell it, copy that. But it's not that simple.
Why not? If it has arms and legs, can't it just mimic the joint movements?
Well, humans and robots are built very differently. We have flexible spines and squishy bodies. They're made of metal and motors. Our joints have a different range of motion. Our center of gravity is different. A movement that's perfectly stable for a trained martial artist might be physically impossible for a robot. It might just tip over.
Ah, so the robot could be trying to copy a move that literally breaks the laws of physics for its own body.
Exactly. Previous methods were pretty good at teaching robots slow, simple motions like waving or walking. But when they tried to learn from data of highly dynamic skills, the AI would often fail because a perfect copy just wasn't possible.
So how did the KungfuBot team solve this?
They developed a really clever two-part framework. The first part is all about cleaning up the motion data before the robot even tries to learn it. Think of it as a quality control step.
A motion cleaner? How does that work?
First, they use a program to extract the 3D motion of a person from a regular video, but then comes the cool part, a physics-based filter. It actually analyzes the movement to see if it's stable. It does this by looking at two key concepts, the center of mass and the center of pressure. Your center of mass is basically the average location of all the mass in your body. The center of pressure is the point on the ground where all the force is being directed, like through your feet.
Okay, so if you're balancing on one foot, your center of mass has to be right over that foot, or you fall.
Precisely. This filter checks if the human in the video is maintaining that balance. If the motion looks physically unstable, like they're about to fall over, the system just throws that data away. It only keeps the good, stable examples.
That makes a lot of sense. Garbage in, garbage out. So it filters for stability. What else?
It also fixes common errors like floating artifacts. Sometimes in the 3D reconstruction, a character's feet might hover just slightly above the ground when they should be planted. The system creates what's called a contact mask to identify exactly when the feet are on the ground and uses that to correct the motion, ensuring the robot stays grounded.
So it's a much cleaner, more physically plausible reference motion. That's part one. What's the second part?
The second part is how the robot actually learns the motion. This is where the team designed what I like to call a robot personal trainer.
A personal trainer?
Yep. They use a learning method called reinforcement learning, which is all about trial and error. The robot tries a move, and if it does it well, it gets a reward. In this case, the reward is for tracking the reference motion as closely as possible.
But we already established that a perfect copy might be impossible.
And that's the key. The researchers introduced something called a tracking factor, which is basically a tolerance for error. You can think of it as a difficulty setting. A large tolerance is like easy mode. The robot just has to get the general gist of the move. A small tolerance is hard mode. It has to be incredibly precise.
So what difficulty did they choose?
This is the genius of the system. It doesn't choose just one. The system is adaptive. It adjusts the difficulty on the fly, just like a good personal trainer would do. When the robot first starts learning a complex move, like a 360-degree spin, the system sets the tolerance high. It says, don't worry about being perfect. Just try to turn around without falling.
So it lets the robot get the basic idea first.
Exactly. Then as the robot gets better and its tracking error gets smaller, the system automatically tightens that tolerance. It pushes the robot to become more and more precise. This adaptive curriculum helps the robot learn these incredibly difficult skills much more effectively than just throwing it in the deep end.
That is really smart. It's a feedback loop. The better the robot does, the harder the trainer pushes it. So the big question, did it work?
Oh, it worked. The results are pretty amazing. In computer simulations, their method, which they call PBHC, significantly outperformed other state-of-the-art approaches. But the real proof is in the hardware.
They actually built a KungfuBot.
They did. They deployed their trained AI onto a real humanoid robot, the Unitree G1. And there are videos of it performing an incredible range of skills. We're talking sophisticated martial arts, jabs, hooks, jump kicks, roundhouse kicks, and also more graceful things like Tai Chi, and even just a full 360-degree spin and the Charleston dance.
Wow, and this was all learned from that adaptive training method?
Yes, and what's really impressive is that it's an example of successful sim-to-real transfer. The AI was trained entirely in a computer simulation. They never had to fine-tune it on the real robot. It just worked straight out of the box. That's a huge deal in robotics because it makes training much faster and safer.
So KungfuBot is real. What are the broader implications of this? It's probably not just for making awesome fighting robots, I assume.
No. Definitely not. This is about giving robots the ability to perform a wide range of complex, human-like tasks. Imagine robots that can navigate complex disaster sites, provide physical assistance in healthcare, or even create new forms of entertainment.
It's a foundational step towards robots that are less clumsy and more agile, expressive, and capable in the real world.
Exactly. The paper KungfuBot shows a powerful new way to teach robots dynamic skills by being smarter about the data we use and more adaptive in how we teach, a huge step forward for humanoid robotics.
A fascinating paper. That's all the time we have for today. Thanks for listening to Daily Papers.